A phase diagram is like a map of the phase of a substance. And by phase, we mean the physical state, gas, liquid, solid. We're looking at pressure versus temperature, pressure on the y-axis, temperature on the x-axis. And we'll see different regions in this phase diagram. And those indicate the conditions where that state is stable. So under this pressure and this temperature, the substance will be stable as a liquid, or it will be stable as a gas. And the lines that separate those different regions represent where the substance is in equilibrium between two states. And so we refer to these as a vaporization curve between a liquid and a gas, a sublimation curve between a solid and a gas, and a fusion curve between a solid and a liquid. The triple point is a place where those three curves meet, and that's a unique set of conditions where you have the gas, the liquid, and the solid all in equilibrium with each other. So here is the phase diagram for water. So here's temperature, and this is not to scale. At 0 degrees Celsius and 1 atmosphere of pressure, we know that water is in equilibrium between a solid and a liquid. And so at that point, it's on the fusion curve. If we reduce the temperature, it's going to just be a solid. If we increase the temperature at 1 atmosphere, it's going to melt and become a liquid. If we continue increasing the temperature, when we get to 100 degrees Celsius at atmospheric pressure, we'll hit the vaporization curve, and that's where water will boil. Above that temperature, you're going to have water in the gas state. Pressure also affects the state of a compound. If we take a liquid, well, let's start with the gas. If we take a gas and we increase the pressure, we can cause it to liquefy. So you can get gas even at a very high temperature to liquefy. This is the triple point where ice, water, and water vapor are all in equilibrium with each other. And this is the point, the critical point, above which you have a supercritical fluid. The line stops here because above this point, you don't have a separation between a gas and a liquid. Any questions? So we can look at different things happening with the phase diagram. And phase diagrams for different substances are going to have different characteristics. The slopes of the lines can be different, and definitely the temperatures and pressures are going to be different. So we can say, well, if we're looking at a temperature change, so we start at 25 degrees Celsius and 1 atmosphere of pressure on this particular curve, what happens as we increase the temperature? Well, it goes from a liquid to a gas. What happens if we decrease the pressure on the liquid? Well, it stays a liquid for a long time, and eventually it'll get to a point where it'll boil. Do you know that you can actually boil water at room temperature? My high school chemistry teacher did this. I wish I could do it. I don't think we have a vacuum pump that's good enough. If you put water in a vacuum flask and pull a vacuum on it and lower the pressure and lower the pressure and lower the pressure, eventually it will boil at room temperature. So you lower the pressure, and eventually you'll get down to the vapor pressure of that liquid at that temperature. When the outside pressure equals the vapor pressure, it boils. So here's this flask of boiling water, and he made us all come up and touch it. And the first person, of course, is like, I don't want to touch boiling water. That's going to be hot. We touch it. It's room temperature. It's just like touching the bench. It's the craziest thing. I have these little snippets of memories from high school, right? Most of it's just this bad blur, right? But that's one of those distinct memories. As we decrease the pressure, the liquid will turn into a gas. Here's iodine and carbon dioxide. Let's go back to water real quick. So here's the fusion curve for water. Notice that it has a negative slope. Iodine and carbon dioxide, that fusion curve has a positive slope. That is more common. Water is not typical in that regard. If we look at iodine, we see that at 1 atmosphere, room temperature would be over here somewhere, I guess. At 1 atmosphere and room temperature, it's a solid. As we increase the temperature, of course, it will melt and become a liquid. If we increase the pressure, we can get the liquid to become a solid. That doesn't happen with water. With water, if we increase the pressure on the solid, it becomes a liquid. That's why ice is so slippery. That's why ice skates work. When you're wearing ice skates, you've got this narrow blade that's supporting all your weight. That puts a tremendous amount of pressure on the ice. That pressure causes the top layer of the ice to melt and makes it very slippery. Other substances don't do that. So iodine has a critical point up here. Carbon dioxide. Here is carbon dioxide's critical point is at 31 degrees Celsius, 72 atmospheres. I'm sorry, I'm distracting myself here. Here's 1 atmosphere. As the temperature increases, it goes directly from a solid to a liquid because this triple point is much higher. For iodine, at 1 atmosphere, you increase the temperature of the solid, it melts first and then becomes a liquid. That doesn't happen with carbon dioxide. You can't have liquid carbon dioxide below 5.1 atmospheres of pressure. It's just crazy.